Okay, welcome everyone. This is the 116th meeting of New Directions in Group Theory and Triangulated Categories. Our speaker today is Juan Omar Gomez from Bielefeld University, and he'll be talking to us about fiberwise building and TT geometry and applications.
Well, thanks for the introduction and also for the invitation. I will start saying that this talk will be based in work in progress, and some other parts of the talk will be based in a recent preprint, but I hope to manage to merge the results that I will present today in a single version soon. Okay, so let me start with my motivation for this talk, and the point is that I would like to classify localizing tensor ideals in certain TT categories arising from representation theory, and in particular, I have interest in study certain categories, let's say like stable categories, derived categories or categories of projective or homotopy categories of projective modules for groups of rings, either finite groups or finite group schemes. And maybe this is the point to clarify that for a finite group scheme, I will mean a finite flat, a finite group scheme. And the point is that I would like to understand this classification of localizing tensor ideals over arbitrary Noetherian bases. And one of the ideas that, let's say, that I have in mind is, or well, motivated by results or recent results of Ikelau and also of Bartel, Benson, Iyengar, Krauss, and Petsova, is that, well, maybe we can understand such classification by looking at the classification of categories of the same nature, but now over fields, and use such classification to basically push it or understand like at the global one. And in my setting, the kind of, as I say, the kind of picture that I have in mind is that I start with a category associated to a group, well, a finite group and a ring R, and then I try to compare it with now a group and now defined over a field. That's why the notation of K. And probably this will be not enough. So one really needs to consider families of functors. Yeah, over certain indexing family. And the point is that such families rarely will be finite. So one need to consider families or infinite families of functors. And the point is like, or the problem is that one needs to glue all this information all together to obtain the information that we want for this guy. And well, in particular, in the case where I'm interested, such functors will arise as or will be induced by base change along the residue fields of the base ring R. And that's why I say, right, like this will be shortly a finite indexing set. So again, as I say, this is just the motivation, and maybe let me try to, well, the talk would have two parts. One will be focused on this abstract nonsense, but then the second part would focus on how to classify these localizing tensor ideals for two categories. One of them would be the category of representations of a finite group scheme over an Noetherian base, and the other one will be for the big derived category of permutation modules, well, finite group over a Noetherian base again. And they would follow a very similar pattern, except that whenever we want to obtain certain topological information of the Balmer spectrum of such categories, yeah, they are quite different. Well, so then let me start with the abstract part. And for this, let me just fix the setup. I'll be considering use rigidly compactly generated TT categories. I'll also refer as big TT categories, which means that I would consider these TT categories with small coproducts. And I will assume that the rigid objects agree with the compact objects, and the smallest localizing category containing the compact objects is the whole category. So examples to keep in mind are derived categories of commutative rings, and well, as I say, I will present in a few minutes a couple more of examples, but for now we can think about that. And also, let me also fix the terminology of a geometric functor between big TT categories. And what it means is that I would consider functors which are exact, strongly monoidal, and that commute with coproducts. Yeah. So for instance, if we take, as I said, the derived category of a ring, a commutative ring, maybe an Ethereum, and I consider the functor, which is obtained by base change along one of the residue fields, right? This will be one of these geometric functors. So great. Why I want to focus on this kind of functors is because they have very nice properties. And I think it has been explained in a paper by Palmer, Delambroyo, and Sanders that such geometric functors have a right adjoint, yeah, which usually will be denoted as F low star. And this functor F low star has itself a right adjoint, which is denoted as F lower shrink. And also this adjunction, this F up star and F low star will satisfy the so-called projection formula, which is a way to relate these elements. I just wrote the projection formula. So for any element X in my category T and any element Y in S, this isomorphism holds. So without further warning, I'll be using this property all along the talk. So just keep in mind that this will hold for all the geometric functors that we will consider. So now, since, as I say, I would like to classify localizing tensor ideals, and there are a few theories in literature which allows to relate such classification in terms of different properties that one can check on the categories. And I basically will center or focus on the one that is referred as BHS stratification. And for this, one needs to impose certain conditions on the Palmer spectrum, certain topological conditions. So the first one, the topological condition is asking that the space is weakly Euclidean, and what it means is that we can see any point on our topological space as the intersection of a Thomason set and the complement of another Thomason subset. So that's precisely what it says, and I just wrote the definition here specifically for the Palmer spectrum of the compact part of the category. And well, maybe I think this is suggestive enough, but I will be using TC to denote the compact part of compactly rigidly generated PT category. And one of the points of asking for such for the existence of these two Thomason subsets is because one can construct. Well, actually, this will work for any Thomason subset. So for any Thomason subset, one has this idempotent triangle. Yeah, so this will work. And using this idempotent triangle, we can construct special objects that will be denoted as GP. These objects are precisely the tensor of EY1 with F Y2. And the point of considering these objects is that they will allow us to see whatever is let's say on the stalk corresponding to the point P in the Palmer spectrum. So that's like the reason to consider these special objects. And well, just to formalize what I say, whenever one has a big TT category with a weakly Ethereum Palmer spectrum, one can define the so-called Palmer-Fabi support for any object in T, basically as the collection of primes in the Palmer spectrum P, satisfying that the associated GP tensor with the object X is non-trivial. And this support will define or will satisfy a number of axioms that I will not mention, but the point is they will behave kind of nicely, except that this Palmer-Fabi support will not satisfy the so-called tensor property, meaning we only have that the support, maybe this will be relevant, the support of the tensor of two objects is not really the intersection of the support of X with the support of Y, but we only have an inclusion. Sorry. Mm-hmm. Well, so now when we have the notion of Palmer-Fabi support, we can then introduce the notion of stratification with respect to the Valmer family support. And this is a definition, well, at least in this generality, by Bartel, Hert, and Sanders, and that's why people refer to this stratification as VHS stratification. But since I will basically just focus on this one, I will just drop the VHS from everywhere. And basically, if we have a big TT category with weakly Noetherian spectrum, then the category is stratified if it satisfies the following two properties. So the first one is referred as local to global principle, and basically what it tells us is that we can reconstruct any object from its stalks, and this is basically equivalent to say that if we consider just this special object GP, and we'll then let P run over the whole Valmer spectrum, then we can reconstruct the whole category. And the second condition is referred as minimality, and it says that for any element, for any prime, sorry, in our category TC, the localizing tensor ideal generated by GP is minimal. And what this means is that if we take a non-trivial object here, then the smallest localizing tensor ideal generated by X is actually the whole localizing tensor ideal generated by GP. Yeah. Okay, but now, okay, what this has to do with my original motivation, which was classifying localizing tensor ideals? Well, let me just make some space. But then, if T is stratified, or well, basically, if and only if this notion of support from localizing tensor ideals to subsets of the Valmer spectrum will define bijection. So this is the kind of classification that I'm aiming for, meaning I'm trying to describe or parameterize these localizing tensor ideals in terms of the Valmer spectrum of the compact part. So, and again, I say I would focus on this notion of stratification during the talk, but at some point I will also make use of a recent notion of a stratification, which is referred as homological stratification. It has been very recently introduced by Bartel, Hert, Sanders, and so. And I will not really explore much of such homological stratification, but I will use some results that they obtain to improve the results that I have somehow. And for that, just let me recall you quickly that we will use the standard notation, I guess, to denote the homological spectrum. And this is the collection of all homological primes in the category of finally presented DC modules, right? Which B is a proper Serre tensor ideal, and those elements are referred. These B's are referred as homological primes of T, and the whole point is that there are special objects associated to each of these homological primes B, which are often denoted as EB, like this, that will replace or will play the role of the object GP that I mentioned in the previous slide. So using these elements EB, which actually have the structure of a weak ring in the category T, one can define a notion of support, but now over any big TT category, so meaning that we don't need to place any topological restrictions on the Valmer spectrum. And the way to do this is that, well, we say that, or we define the homological support as the collection of all Valmer prime, homological primes satisfying this condition. So the internal home of X with this special object EB will not vanish. Maybe it's interesting to say that, well, depending, these are also pure injective objects in T. Okay, so now we already know the concept of stratification whenever our category has weakly Noetherian spectrum. And as I say, well, this basically is because we need such condition to define Balmer-Fabry support, but now we have a notion of homological support for any TT categories. So their definition is very natural. So as I said, this is the new notion of homological certification. So if you have a TT category, a big TT category, then one says that T is homologically stratified if it satisfies the analogous properties. So the first one is the homological local to global principle, which means that we can reconstruct the monoidal unit using all the special objects EV. And the second one is minimality, but now for the localizing tensor ideals generated by EVs for any V in our homological spectrum. And again, the conclusion that we had before, that this helps to classify localizing tensor ideals, will hold. So the theorem also of the same for authors is that this notion of homological support will define, well, T will be, maybe, let me write it here. T is homological stratify if and only if the homological support defines bijection between localizing tensor ideals with subsets, but now of the homological spectrum. So in principle, this notion of stratification is much more general because, as I say, we don't really place any restriction on the Balmer spectrum. However, I'm not aware of any category which is homologically stratified that is not stratified. Now, so the natural question is, well, if I already know that the Balmer spectrum of my category is weakly Unitarian, how I can relate these two the notions of stratification, and the answer is also given by the same four authors, and I will just put it here and state it here. But the point is, we need to recall the Balmer's conjecture, which is known as the Nerves-of-Steel conjecture, and there is always a comparison map between homological spectrum with Balmer spectrum that is always rejected, and the conjecture is that this map is always injective. So I will just use the term the Nerves-of-Steel conjecture to refer to this property, or well, to this statement. And now the theorem that I mentioned by Bartel, Hertz, Sanders, and so says that if we have a big TT category which has a weakly Unitarian Balmer spectrum, then stratification is equivalent to homological stratification plus the Nerves-of-Steel conjecture. Yeah. So basically, well, I think this is all for the preliminaries. So for, let's say, like the rest of the abstract part will be split in two. One of them is like some very basic observation that we can make out of the following definition, but the rest of this first part will actually depend on this age of stratification. So that's the only warning. Anyways, then let me start with a family. Well, sorry, with a set I. Let me fix it and consider a family of functors of this form. So I will say that this family of functors is weakly descendable if we can reconstruct the monoidal unit using the right adjoints of Fi star. Maybe some pointers here. The first one is that the terminology is not due to me. So I just took the terminology from the paper of BHS set. But I'm not sure who came up with this terminology, so I will just adopt it and use it. And also, let me give you an example when we have this sort of family of weakly descendable functors. So if we can consider for any, maybe let me fix it, a commutative ring, commutative Newtonian ring, then we can consider this family of functors, again, even by base change along the residue fields. Right. from the R to the KP. And this will be indexed over the spectrum of R. So this is weakly descendable. And this basically follows by Niemann's stratification theorem. And well, I think it's the case to keep in mind, because I will use actually this result to define a family of weakly descendable functors in the two settings that I'm interested in. Okay, so the first consequences of this definition is as follows. So the first one is actually a very, very easy observation, and is if we have, and well, I need to make it a bit smaller. This property is known as building, and the point is, if we have a family of weakly descendable functors, well, I'm always assuming that my functors are geometric, so I have a family of weakly descendable geometric functors, and then one can basically describe the localizing tensor ideal generated by an object Y as follows. So we need to check that the image under Fi of any object lies in the localizing tensor ideal of Fi of Y for any I in my set. So if this property holds, I mean, this property, sorry, it's known as building, and it will hold immediately if we assume that our family is weakly descendable. And this basically follows. So the idea for this is actually the projection formula plus the fact that this guy commutes with coproducts. So it's a very easy observation, as I say. And the point is, if we want to also make the dual statement, meaning like we would like to reconstruct in a way colocalizing ideals generated by an object, we can do it, but we have to replace our geometric functor F star by this F lower string, which is the right adjoint of F star. This property will not play a role really in the talk. That's why I will decide to omit it, but maybe it's worth to keep it in mind that it's also whole. And one of the immediate consequences that we can get out of this property of building is that we deduce that a family of weakly descendable functors has to be jointly conservative. And well, the same will hold for this family of functors. And now, a very nice result of Bartel, Castellana, Hert, and Sanders will tell us that there is, or well, the map induced on Balmer spectra from TIC to the Balmer spectrum of TC is surjective. And actually the same, well, let me clarify that this coproduct is taken in the category of topological spaces, and a similar statement will hold for the homological spectrum. Yeah, so actually they prove the map is a surjection on the homological spectrum, and then they deduce the statement about the Balmer spectrum using the surjectivity of the comparison and also the naturality. Well, anyways, we will use also this fact in a moment. So, but now just considering the definition, we obtain this, as I said, this very basic observation, and we already obtained some topological information about the Balmer spectrum, but also about the functors. And I say that the result that motivates everything, or at least like motivate me to think about this kind of problems, is the following. And since I will focus now from now on in stratification, I will fix, or I will assume, sorry, that all my categories have a weakly Noetherian spectrum. And the theorem says that if I have a family of weakly descendable geometric functors, which satisfies that every or each TI is stratified, but also the previous map that I draw is injective, then I can obtain that this is stratified. And this is somehow the motivation for the Fiberwise, like it's kind of These functors are just kind of the fiber over I, and then if you can prove that in each piece, your category is stratified, then you somehow glue all this information because there is not much gluing in some sense, right? Like everything is happening in fibers. And I think this is interesting enough because it applies in some of the result or some of the applications that I will present later, even though I will present a more general statement. And the point is that this is actually very easy to prove using building. So if we want to check that the category T satisfies the local to global principle, then one only have to remember that the image of Fi or under Fi star of one of these special objects, GP, corresponds either to 0 or to GQ, where now Q is the image. Sorry, it's an object such that under the map induced spectra hits my point P, and it's 0 otherwise. So if we keep this in mind, then we can use building, well, first the local to global principle. Oops. So basically by this condition on the map, we can deduce that the monoidal unit is basically in this guy, EQ, such that Q is in the spec of TI compact, right? And now we apply building. So building will give us that then the unit must be, yeah, because the point is all of these elements will be the image of one of the GPs coming from spectrum of T. Then we deduce that this is in log tensor. Just one moment of GP, but now P is in the Balmer spectrum of T. See. So this immediately gives us the local to global principle, and actually with maybe a little bit more of effort, one can prove that the local to global principle descends along quickly descendable functors, but this is good enough. And if we want to check—
Excuse me, could I ask you something?
Yes, sure.
Do you need the injectivity of the whole map, or do you need the injectivity of each of the map?
Yeah, in principle, the injectivity of the whole map. I mean, for the local principle, for the local to global principle, it's really not necessary, the injectivity of the whole map, but for minimality, it is.
Okay, thank you.
So now the minimality condition is, we need to take a point, an element which is non-trivial, right, in one of these guys. And again, since I'm assuming that my family is weakly descendables, in particular is jointly conservative, and this assumption again, then there exists a unique I, such that if I star of X is non-trivial and belongs to localizing tensor ideal, but now over Fi star of GP, but this guy is just GQ for a Q like this. And now we apply minimality for Ti, which tells us that then, well, minimality plus building, which tells us that GP must be in log tensor of X. So hence we conclude minimality. And as I say, this is a very easy consequence of building. But now I want to generalize this. And in order to generalize this, I really need to look into this H stratification. So that's the content of this second part of the first part. So now let me jump to the rest. So the rest will actually depend on this homological stratification. Let me just remind you some formulas or of the support along base or geometric functors. And the two of them are very similar. One of them is for the homological support. The other one is used for Balmer-Fabry support. And I will fix a weak ring in my category S. And if I assume that my category S has the homological detection, meaning that the support, the homological support of an object is empty if and only if the object is trivial. So this is what it means, detection. So if this property holds, then I can describe the homological support in T of the push forward of this weak ring W as the image of the support in S of the original element of weak ring W under the map induced on homological spectra by my geometric functor F. This has been proved in the paper of homological stratification, so this appears here. And the analogous property has been proven in the paper by Bartel, Castellana, Hert, and Sanders about co-support in TT geometry. I don't remember. So, well, I think I remember that this is theorem 13, and I think this is 6 point something, but I don't remember. So now the point is that if we have these formulas, we can describe, or we can basically, describe the support of weak rings in our category T for weakly descendable functors using the whole family of maps induced on either in Balmer spectra or on homological spectra. So again, fix a family of weakly descendable functors and assume that each category has the H detection property, then we can describe the support of a weak ring in T as the union index over all, or initial sets I of this image. Yeah? So somehow this will, well, maybe it doesn't look easier, but it will help us to describe actually, or to say how the Balmer Fabi support relates with the homological support for categories with weakly Noetherian spectrum. So just keep in mind these two properties. And well, of course, one is obtained by this point in this recollection, and the other one is obtained by this point in this recollection. And maybe you wonder why I'm just assuming homological detection, and it's because so homological detection implies detection, and this is a result again by the 4 authors that I mentioned already. So yeah, so it's enough to assume H detection. Now with this in mind, we can prove the following, and as I say, it's just an explicit description on how we can relate Balmer-Fabi support for weak rings with the homological support. So again, if we have a family of weakly descendable functors, and if we assume that every category Ti on this family satisfy the H detection property and also the nerves of steel conjecture, then we can relate the Balmer-Fabi support with the homological support for any weak ring in your category T. And let me give you the idea. And the idea is kind of simple now, using that we have these formulas, so we can basically do diagram chasing in this commutative diagram to prove that this equality holds. So maybe let me write that these maps are induced by the homological, sorry, the maps induced on homological spectrum, and this in Balmer spectrum. This is the comparison map between the homological spectrum of T with the homological spectrum of, with the Balmer spectrum of T. Sorry, I forgot to put the C's here. And this is the map induced by the comparison map in each of the categories Ti. So just using the commutativity of this square, using that this map is surjective, and also that this map is surjective, the previous formula, we can obtain this equality. Now, with this equality, we can basically descend the nerves of steel conjecture along weakly descendable functors. Yeah? So the point is, if we have a family and of weakly descendable geometric functors, and if we assume that each Ti satisfies H detection plus the nerves of steel conjecture, then we can conclude that the nerves of steel conjecture holds for T. And what's the idea behind this result? Let me just explain it. So we can prove then that the tensor formula holds for weak rings. And this is basically using the previous lemma and the surjectivity of the comparison map. And then there's a result by Bartel, Hert and Sanders, which tell us that the tensor formula for weak rings implies the nerves of steel conjecture. So then we obtain nerves of steel conjecture for there. Now we're almost there. And now we obtain a really nice generalization of the previous theorem that I showed. And is that if we have a family of weakly descendable functors, and if we assume that each Ti is stratified, then we can obtain that our category T is stratified. So it's a huge improvement now. And the idea is that, well, again, the four authors prove that T is H stratified. So basically, homological stratification descends along weakly descendable functors. And the previous theorem, which tells us that also the nerves of steel conjecture descend along weakly descendable functors, then we can apply one of their main results, which tells us that homological stratification plus the nerves of steel conjecture is equivalent to stratification. So with this, now, as I say, we obtain a huge improvement of the previous theorem, but this relies on homological stratification. We're almost there. I mean, this almost concludes the first part of the talk. And basically now I would like to move to the specifics. Like I would like to tell you how we can apply this theory now to describe or well, to obtain stratification for two categories of interest. And for that, one needs to, well, okay, so we define weakly descendable, family of weakly descendable functors, but how we can actually prove that a family is weakly descendable. And well, that part is not too easy. But for instance, if we're lucky enough, we can find like a discard kind of diagrams. So let me just explain a method. So if we have again, set I, and if we assume that for every element in my set, we have a diagram of a commutative diagram, commutative functors, yeah, like this. And if we assume that this square is horizontally right adjointable at the monoidal unit, which means that if I take the monoidal unit here, yeah, and then take the push forward of this map along the right adjoint of Fi, so meaning a flow start of 1i, and then project it down to using this tau star, then it is the same as going from here. So this is basically, since I'm assuming that it's a geometric functor, it will be just a unit here. But now I can just push forward along the right adjoint of gi star 1i. So this right adjointability at the monoidal unit means that this is an equivalence. And just I'm not entirely sure if this will imply that the whole square is right adjointable. But it's enough for my purpose to assume that it is at the monoidal unit. So with these conditions, if I have this family, and if I have the property that, oh, okay, I need to make this smaller. And if I have that this Fi's determine a family of weakly descendable geometric functors, then I can deduce that the family Gi is weakly descendable. So in fact, I picked the letters kind of in a suggestive way, and I will relate it to the example that I gave with Neumann's stratification theorem. So meaning that I will use derived categories here, and the categories that I am interested are those. So basically I will reduce the problem to check right adjointability at the monoidal unit for the examples that I care about. Okay, so now we have arrived to the main examples, and I will consider, as I say, two different categories. I will follow a kind of similar pattern. And for that, again, just let me remind you that R denotes a commutative Noetherian ring, and G denotes a finite group scheme or a finite group scheme defined over R. And under this assumption, I would consider the category, well, the big category, the big derived category of permutation RG modules, which is defined as follows. So this category is also known as the small derived category, and we'll just use this to denote it. So one consider the homotopy, the bounded homotopy category of finally generated permutation RG modules, then this symbol means that we idempotent complete this category. And we can consider this category inside of the full homotopy category of all permutation RG modules. And in there, we close this small derived category by coproducts. So in other words, the definition of the big derived category is use the localizing category generated by this guy inside the homotopy category of permutation RG modules. And this category has tensor product, which is induced by the tensor product over the ring R with the diagonal action of G. So with diagonal action of G. And sorry, I'm just checking the time. So with the diagonal action of G, this will determine a big TT category, and this is something that has been proved by Palmer and Galloway. So this is a result of them. And we will consider this category. And the second category that we'll consider is the so-called category of representations of a group scheme over R. And this is defined as the incompletion of the bounded derived infinity category of finally generated RG lattices. So I will not really give much details about this guy, but let me say that whenever R is regular, this category is basically the homotopy category of projective RG modules. And so that's maybe the example to keep in mind. And of course, since again, the tensor product will be induced by the same guy, so meaning the tensor product over R with the diagonal action of G. And maybe let me just say a few words about the compact part. So the compact part is this guy, and as I say, is the bounded derived category of lattices. And what it means is that we consider this category of lattices as an exact category where the exact structure is induced by the split exact structure of projective R modules. Yeah, so one can define the derived category of an exact category. And as I say, I mean, these two categories or these two examples will follow kind of a similar pattern in what follows. So I will just write TER to denote any of those two categories whenever I don't need to make a difference between them. And the point is that now we want to construct a family of right adjointable, of these squares which are right adjointable at the monoidal unit, where we already know that one of the top functors will satisfy weakly descendability. So now let's consider the spectrum as the spectrum of the ring as our indexing set. Let's pick a prime there, P. Then we can construct a commutative square of geometric functors as follows. So this map is the one that has already appeared, meaning that this is the one induced by base change along the residue field. And this one is also induced by base change along the residue field. So it's also induced by base change along this residue field. And these horizontal maps are induced by this and this are induced by the augmentation map. And here, well, this guy is the algebra of measures of my group scheme, or just the group algebra for G affine group. And I always have this augmentation map, so hence I can consider this restriction functor, which is really some sort of inflation functor. With this, I can prove that this is a commutative square. All the functors are geometric, and now the proposition is that this square actually satisfies right adjointability at the monoidal unit. So this is a hard task. So this is one of the technical things to check, but it's something that one can do. And actually, I have to say that Paul Walmer is the person who gave me this idea. so thanks. So yeah, so one need to check that going in this direction is commutative, at least for the monoidal unit. So we're almost there. I mean, we already, I mean, as I say, this family of functors is weakly descendable by Niemann. Then, since these squares are right adjointable at the monoidal unit, we deduce that these functors are weakly descendable as well. So then we're almost there to say that then our two categories are stratified, right? These two categories. However, we still need to say some things about the topology of the Balmer spectrum. And maybe this is a very good point to say that the stratification for this guy is known in this generality, and this was something that was proved by Bartel, Benson, Iyengar, Krauss, and Petsoma. And they use the so-called BIK stratification, which is a stronger notion. However, as I say, since these two categories follow a very similar pattern, I thought that it was worth to include a different approach to stratification for this guy. And for this category, the big category of permutation modules, the stratification is known for the field case, thanks to Balmer and Galloway, and well, pushing to an Artesian base will be a new result. So well, as I say, we still need to say something about the topology of the Balmer spectrum. So again, if we fix, well, this part will be very different for the two cases. So we fix a finite group scheme defined over a commutative Artesian base, R. And now the task is actually to prove that the comparison map from Balmer spectrum to the homogeneous spectrum of the endomorphism ring is an homeomorphism. So this guy is actually this graded endomorphism ring of the monoidal unit in this category, and that identifies with this graded ring, which is used basically rational cohomology. And the point is, if we manage to prove that this is an homeomorphism, thanks to a result of van der Kallen, we know that this graded ring is finally generated as an algebra over R, and hence we can deduce that this is an Artesian space, and we obtain the result that we want about the neutrality of the spectrum of DB mod GR. And since I think I have 10 minutes, I will just say very quickly that, well, one needs to find an argument that gets around BIK stratification to prove that this comparison map is an homeomorphism. But the idea is the one, actually, it's the same one as the one given by Bartel, Castellana, Hert, and Sanders in the short paper of the surjectivity of a map in Balmer spectra. And it's basically that one can compare, say, like at these functors. Let me just write dB of G Kp, yeah, with the spec of dB G. Of course, one has to also write the base change of the group scheme, but let me forget about it. And one can complete this to a square where one compares with the the homogeneous spectrum of now the cohomology in this case, which is GKP, the coefficients in Kp. And this is compared with the homogeneous spectrum of the cohomology of G with coefficients in R. And the point is that this is a bijection, yeah, and this is, I think, is a result of the AKP. And this is a result that this is also a bijection by a result of BBIKP. This is always surjective by a result of Balmer, and this map is also surjective because of the jointly conservativity of our functors. So one obtains that this map is a bijection, and hence this is also a bijection. And now one uses Eike's law result to say that, well, bijection of the comparison map from an Artesian category has to be an homeomorphism. So that's how one proves that this map is an homeomorphism, and then we obtain basically stratification in the case we care. And now let me jump to the neutrality of the Balmer spectrum of the category of permutation modules. And this one is, I would say, well, I already say that it's different, and it's because we maybe try to compare with the endomorphism ring of the monoidal unit, but this one is in general not enough for this case, explicitly because even in the field case, if you compare with the endomorphism ring of the monoidal unit, you will obtain that this agrees with the spectrum of the field, which is just a point. So this really doesn't carry as much information. So we really need to find a different way to prove that this is Noetherian. And just let me briefly recall what was the idea of Balmer and Gallagher to prove that this space is Noetherian in the field case. And basically they combine two functors. So the first one is very general. It exists not only for fields, but for any coefficient ring. And then they show that there is a localization functor from the big derived category of permutation modules to k inch of kg modules. Yeah. So this is one of the functors they use. And the second functor is that for any p subgroup, h of g, they define a geometric functor referred as modular h fixed points, where it's a way to compare these derived category permutation modules of g with the one of the Weil group of h and g. So now using these two functors, they basically managed to prove that this family of functors, let me just spell this out for you, basically from kg to k Weil of h, and now using the localization, so to basically to dB of k Weil g of h, this family of functors index over this category of, sorry, this collection of subgroups, of p subgroups of g, will determine a conservative functor, not using the small part, but also the big part. Hence, you obtain a surjection of Balmer spectra, and you already know that this space is Noetherian, so you conclude that this is Noetherian. So it's somehow the rough idea, just to prove that, that the spectrum is Noetherian in this case. But then how we can generalize this to more general coefficients? And well, the problem is modular fixed points, of course. And as the name suggests, it's something that is attached to the characteristic of the field, dividing the order of the group. And yeah, I think it's hard to extend this notion of modular fixed points as a functor, but still there is a way to fix it and get around of this problem. And for that, just let me maybe remind really quick how one can construct these modular fixed points. And let me just start with the normal case. So if you fix a normal subgroup, P subgroup of G, then Balmer and Gallagher show that this composite, where this map is given by inflation, and this one is a quotient map, where this category is basically use the additive closure of modules of this form, G mod H, where where N is not contained in H. So this is a monoidal equivalence. It's even a monoidal equivalence if you only consider these additive categories of permutation modules. So using this, they can basically construct a functor. Again, let me just think in this case. So from kg to basically this quotient, right? K, maybe let me refer as k tilde of g. So to k tilde of g. And now you can use the inverse of this equivalence. So maybe let me refer to this as f to compare it with k g mod n. So this map is a modular fixed points. And yeah, of course, if you go through the whole construction, you will see that really the characteristic of the fields plays a very important role in proving that this is an equivalence of categories. But well, maybe one can get around of this, and the way that I propose to get around this problem is that, well, we might not be able to invert this map on categories, but we can do it on Balmer spectra. So the point is that if we consider now the same composite with general coefficients, we can still invert this map after applying Balmer spectrum. So now we have really a way, maybe, oops, in the general case, right? We cannot go from k tilde g to k g mod n. So it's the other way around, right? Like the map that we have, which is the composite of inflation with the quotient. And the problem is that we cannot go the other way around. But if we apply Balmer spectra, then we have a way to compare. Maybe let me just write it here. So now I have to invert the arrows. Right? So we would like to compare the bottom with the top. But since I say one can prove that this is an homomorphism, then we can use the inverse of this guy. And the upshot is that we can use these maps. I use define it as triangular H fixed points to basically extend Balmer and Gallagher idea to prove that the Balmer spectrum in this setting is still material. So now we have all the ingredients that we need, and we can conclude that both of our categories TGR are stratified. And well, I think that's all I wanted to say. Thanks.
Thank you very much, Omar. That's all. Please speak a round of applause. If you have any questions, please ask them.
I guess I have a question. So do you know that, hi, do you know that the map, so in the slide before you showed this map is an isomorphism Balmer spectra. Do you know if it is also TT equivalence?
Which one?
Yes, so you said that this composite is an homomorphism Balmer spectrum. Do you know or you don't know if
no.
If it is,
I don't have a contraexample, but I believe it's not. At least it's not for this category. So if you only consider these additive categories of permutation modules, then it's not. So I'm not sure what happens once you apply the functor KB. I don't know if you can correct it. It's something that I don't know, but I think you cannot. Yeah.
Okay.
Thank you, Luca. Any more questions?
So the results you obtained typically when you have a ring of coefficients and you're playing with the residue field of that ring, is there any chance of formulating things with a TT category over base and playing with the residue field of the base at the level of tensor translated categories without having a ring around and actual fields, but having everything in TT geometric terms?
Yeah, I mean, that's something
maybe not construct the things because it's always difficult. I mean, of course, our infinity category friends might have answers, but maybe formalize what it means to have. Or perhaps that's what you got. That's what you had with the base change square.
Maybe this is the closest thing, right? But I'm not entirely sure. Yeah, I mean, I thought about it like for a while, and I couldn't generalize this further. So the best I can get is something like this.
Thank you, Paul. Any more questions? Anyone? So which is the part that's work in progress? And there is a preprint, and you said some things to
yeah. So basically, the part that so there's a part where I mentioned, right, that you need to impose certain extra assumptions on your family of geometric functors to obtain the theorem, right? The theorem that I mentioned at the beginning. So meaning, maybe let me go back and back. Oops, I think I went too far. So the point is, like, one can use this theorem to prove or to deal with the applications I mentioned. And this is what you can find in my current preprint. But the point is, I realized that one can generalize this using this homological stratification, and that's the part that is not included in this version. I think it was kind of parallel in a way. I mean, I didn't know about their work, and yeah.
Okay. Okay. There's a message in the chat. Oh yeah, sorry, Natalia sent you to go. Okay. Any more questions? Anyone? Right, if we don't have any further questions, let's thank Omar once again. Thank you all for coming. We have Martin Kalk from Gros speaking next week. Bye-bye.
Bye.
Thanks. See you.